Ever wish learning could be like way faster? Like you could just absorb knowledge and get those aha moments without all the struggle.
Yeah, like turbocharged learning, right?
Totally. Well, today we're diving deep into something that might actually change how you learn from, well, pretty much anything you read.
Ooh, okay, I'm intrigued. Hit me.
It's all about feedback, but not just the surface level, did I get it right or wrong kind of feedback.
Right, because there's got to be more to it than that. I mean, we all know just seeing a grade doesn't magically make us understand something better.
Exactly. So we're going to go deeper. We're going to look at the actual mechanisms of how feedback really works in our brains. Think of it like decoding the instruction manual for your own learning.
I like that. An instruction manual for the brain. So where are we getting this super secret knowledge from?
Well, our guide for this deep dive is a fascinating research article from 1989 called Get Ready for It, Feedback in Written Instruction, The Place of Response Certitude. It's by Raymond W. Colhavy and William A. Stock, and it was published in the Educational Psychology Review. And don't worry, we'll unpack all the jargon.
Appreciate that. Jargon can be a real brain blocker sometimes.
Absolutely. Our mission here is to understand how feedback, specifically when you're learning from written stuff, really impacts you, going way beyond just a simple good job or try again.
So, like, how does feedback really sink in and change what we know? I'm ready to get to the bottom of this.
Me too. So to get there, we're going to take a three-stage journey. First, we'll explore this older idea of feedback being purely about reinforcement, like a reward system.
Okay, that makes sense. Like, if you get something right, you get a gold star, so you're
Yeah.
more likely to do it again. Classic conditioning stuff, right?
Exactly. Then we'll move on to how the thinking evolved to see feedback more as information that our brains use to adjust and improve.
Ah, so it's not just about being right or wrong, but about using feedback to guide our learning. Makes sense.
Yeah. Exactly. And finally, we'll get into this super interesting model that the authors propose. It brings in this concept of how confident you are in your answers and how that interacts with the feedback you receive.
Ooh, I like where this is going. Confidence definitely plays a huge role in how I learn. Like if I'm super sure about something but then get it wrong, it throws me off way more than if I was already kind of unsure.
That's exactly the kind of thing we're going to explore. So
Yeah.
let's kick things off with that old school view of feedback, the reinforcement era. For a long time, the dominant idea was that feedback's power came from reinforcing, strengthening those correct responses.
Right, the classic reward system. Do the right thing, get the reward, and you're more likely to do it again.
Precisely. This view really stemmed from operant psychology, with B.F. Skinner being the big name there. Think back to those early teaching
Oh
machines.
yeah, those things. Like you'd answer a question, and if you got it right, the machine would ding or light up or something. Very basic.
Exactly. So the thinking went, your response to a question in some learning material, like a textbook or a quiz, was basically like a lab animal pressing a lever.
Okay, so we're lab rats now. Interesting analogy.
Well, bear with me. And then, if your answer was correct, the feedback, that ding or the correct mark, was basically the reward, like the food pellet the rat gets for pressing the right lever.
So right answer equals treat. Got it. But I gotta say, even back then, some researchers weren't quite buying it.
Oh, yeah, definitely. There was pushback even in those early days. People like Anderson and Nett and Holding, they were like, hold on a second, is writing a complex answer really the same as a rat pushing a lever?
I mean, I see their point. A rat's not exactly thinking deeply about its lever-pressing choices, right?
Exactly. So out of all this debate came the standard way that researchers started investigating feedback, which was through this thing called the three-cycle paradigm.
Three-cycle paradigm. Sounds complicated.
It's not as bad as it sounds. Basically, it goes like this. First, you get the instructional input. So that's the lesson, the reading passage, the problem you're trying to solve.
Okay, so the stuff you're supposed to learn from.
Right. Then you, the learner, give a response. You answer the question, write the essay, solve the problem.
Makes sense. Input, response. What's the third cycle?
The third cycle is where the feedback comes in.
Mm-hmm.
You find out if you were right or wrong, you get an explanation, you see the correct answer, whatever form the feedback takes, and often there's a post-test later to see how well you actually learned.
So it's a complete learning loop. And this is how most research on feedback is structured.
Pretty much, yeah. And the key thing about this three-cycle paradigm is that it's not just about the materials and the feedback itself.
It's also about the learner, right? How
Yeah.
we perceive and understand things, how we react to the feedback.
Exactly. Now, you can kind of see where the confusion started, right? This three-step process, learn, answer, get feedback, it looks a bit like that simple reward system. But as the article points out, Humans are way more complex than lab animals.
Yeah, thank goodness for that.
Right. We're not just responding to simple stimuli in a controlled environment. The things we learn, the ideas, the concepts, they're always changing, evolving, connecting to other things we know.
And our responses, even if it's just a multiple choice answer, usually involve some kind of thought process, not just an automatic reaction.
Totally. But get this, even as late as the 1980s, this simple reinforcement view of feedback was still hanging around in textbooks and articles about education. The article even mentions Skinner himself talking about it in 1986.
Wow, that's kind of surprising. You'd think people would have moved on by then.
Right. It's kind of amazing how long that basic idea persisted, even when it didn't fully explain what happens when we learn. But that brings us to the next big shift in thinking, feedback as information.
Okay, so less about treats and more about data. I'm ready for the upgrade.
Me too. This new view emerged as we learn more about how our brains work, especially from the perspective of information processing.
So how is this information processing view different? What's the key distinction here?
Well, a big part of it is understanding the difference between what we call open loop and closed loop systems.
Ooh, systems thinking. I'm always up for some systems thinking.
Right. So that old reinforcement idea is basically like an open loop system. It's just a straight line from input to output. The system reacts, but it doesn't really use the incoming information to change what it's doing.
Okay, I think I get it. So like a vending machine, you put in your money, you press the button, and you get your snack. End of story. The vending machine doesn't learn anything from the transaction.
Exactly. Or a simpler example, a toaster. You put in the bread, it toasts it, and that's it. No feedback loop to adjust the toasting time based on how dark the bread is getting.
Makes sense. But human learning, especially with feedback, is way more like a closed loop system, right?
Absolutely. Think of a car's cruise control. It gets information about your speed, compares it to what you set it at, and then tells the engine to speed up or slow down to maintain that speed. We, as learners, do something similar. We take in the information from feedback and actively use it to correct our mistakes, adjust our understanding, and improve our performance.
So we're not just passively receiving feedback. We're actively processing it and using it to adjust our internal models. That makes way more sense.
It does, right. And the work of Telezina really highlighted this crucial difference in how we learn. Now, in an open loop system, errors are almost irrelevant. The focus is all about getting the correct response and reinforcing it.
But in a closed loop system, errors become super important because the system is designed to learn from them and correct them.
Exactly. And this shift in thinking had a huge impact on research. It led to a ton of studies focused on understanding how people correct errors and how feedback can best support that process.
So researchers like,
Oh, yeah, tons of them. Anderson and his colleagues, Ellie, Gilman, and of course, Kolfavi and Parsons, the authors of our main article here. They were all key figures in this move towards understanding feedback as information for error correction.
that makes sense. And this new way of thinking also helped explain some things that the old reinforcement view just couldn't, right?
Totally. One of the big ones was this thing called the delay retention effect, or DRE for short.
Delay retention effect. Okay, break that down for me.
Basically, it's this really interesting finding where you actually remember information better if you get the feedback a little while after you first try to learn it.
Wait, really? So waiting to find out if I got it right actually helps me remember it better in the long run. That seems counterintuitive.
It does, right. And this was a real head scratcher for the reinforcement folks. Because in a purely reward-based system, a delay between doing something and getting the reward usually makes the learning weaker.
Makes sense. Like if you give a dog a treat 5 minutes after it sits, it's probably not going to make the connection as strongly as if you give it the treat right away.
Exactly. But the information processing view offers a different explanation through something called the interference perseveration hypothesis.
Interference perseveration hypothesis.
Okay.
Okay, you're going to have to break that one down too.
Basically, the idea is that when you get delayed feedback, those initial mistakes you might have made, they kind of fade from your memory a bit.
So it's like your brain has a chance to clear out the wrong answers before getting the right one.
That's the gist of it. And when you finally do get the feedback, it's easier to learn the correct information because there's less interference from that old incorrect stuff.
Oh, that's interesting. Like the delay gives your brain a chance to reset before taking in the new information.
Right. There's also the idea that, if you've just been really intensely focused on a task, your brain might not process the feedback as effectively.
It's like, okay, brain, take a breather, come back in a bit, and then we'll see what we got right and wrong.
Exactly. Now, some researchers who did a lot of work on this, there was Brackbill and colleagues, Moore, Sassenrath and Young and Sturges, they really explored this delay retention effect.
So there's a good amount of evidence that this delayed feedback thing actually works.
Yeah, there is. And while this specific interference perseveration hypothesis might need some tweaking, as suggested by Peake and Telema and Fay and Andre, the overall evidence from these delay retention studies really showed that feedback is more than just a reward.
It's about giving our brains the information they need to adjust and learn.
Precisely. And this shift in thinking really pushed research towards looking at how different types and amounts of feedback could lead to better learning outcomes in the end.
So less about just saying good job or try again, and more about understanding the nuances of what makes feedback effective.
Exactly. And that brings us to this really important idea of initial response characteristics. Because, just saying an initial response is right or wrong is kind of oversimplifying things, right?
Totally. It's not a black and white situation. There are shades of gray in how we understand things, especially when we're learning something new.
Right. Like, you could get an answer right, but it could be a total fluke, just a lucky guess.
And on the flip side, you could get an answer wrong, but it might be because of a tiny misunderstanding, or it could be a sign of a much deeper conceptual problem.
Exactly. And this is where that concept of response certitude comes in.
Response certitude. Remind me what that is again.
It's basically how confident you are in your answer, how certain you feel that you've got it right.
Ah, okay. So it's not just about the answer itself, but about how sure you feel about it. That makes a lot of sense.
It does, right. And this brings us to another crucial point. That assumption that if you get something right initially, it's automatically locked in your memory. And if you get it wrong, feedback will easily fix it. Well, it turns out that's not always true.
Oh, really? So even if I ace a test, it doesn't mean I'll remember everything perfectly later on.
Unfortunately, not always. People can forget things they initially got right. And sometimes, feedback doesn't actually correct those initial errors. There's research by Lyle and Kolhavi and Peake and his team that shows this happening.
So just because you nailed it the first time doesn't mean it's permanently stored in your brain, and getting feedback on a mistake isn't a guaranteed fix.
Sadly, no. And this is where how confident the learner feels about their answer becomes really important. This response certitude actually plays a big role in predicting how effective the feedback will be. Kolhavi's 1977 review paper really highlighted this.
So if I think I'm right, even if I'm actually wrong, that might change how I take in the feedback.
It can, yeah. It might make you more resistant to accepting the correction. Or if you were right, but just guessing, you might not pay as much attention to the feedback and not really solidify that knowledge.
So it's not just about objective correctness. It's about our subjective experience of how sure we are. That's fascinating.
It is, right. And it also means that the goals of feedback are different depending on whether you got the initial answer right or wrong. If you got it right, the goal is to help you remember it better, to strengthen that connection in your brain.
So in that case, the feedback is more like a confirmation of what you already know,
Exactly. But if you got it wrong, the feedback has a much bigger job to do.
because it needs to help you unlearn the wrong thing, learn the right thing, and make sure you remember the right thing going forward.
Precisely. And the article argues that not paying attention to this difference between the needs of correct and incorrect responses is a big reason why research on feedback has often had such mixed results.
That makes a lot of sense. We're treating all feedback the same when it actually needs to serve different purposes depending on the learner's initial state.
Exactly. So we can't just think about right and wrong as the only factors. We need to bring in that element of learner confidence. Now let's move on to the actual components of feedback itself. You mentioned earlier that it's more than just a yes or no, right?
Oh, absolutely. There's a whole lot more going on beneath the surface. And the standard three-cycle model that we talked about, that provides a good framework for analyzing most learning situations.
Right. Input, response, feedback.
Exactly. And when we look at feedback research, a lot of it involves manipulating either the materials or the timing of the feedback within those three cycles.
So, like, giving feedback right after each question versus waiting until the end of a whole lesson.
Precisely. Both are technically immediate in a sense, but they happen at different points in the learning process, which can impact how the information is processed.
Makes sense. And then there's the delay retention effect research, which specifically looks at changing the time between the initial response and the feedback to see how it affects long-term memory.
Right, so timing's one key aspect. But what about the feedback message itself? Can we break that down further?
We can. We can think of the feedback message as having two main components: verification and elaboration.
Okay, verification and elaboration. Let's unpack those terms.
So verification is the most basic level. It's simply telling you if your answer was right or wrong.
Yeah.
It's the yes or no, the check mark or the X.
The bare minimum, just
Yeah.
confirming or denying our initial response.
Exactly. And the article suggests that this verification aspect is actually the first piece of information we process when we get feedback, which makes sense, right?
Yeah, it's like our brains are immediately looking for that confirmation or rejection signal. Was I right or wrong?
Exactly. And then after that initial verification, we move on to the elaboration part.
Okay, so elaboration is everything else, all the extra information beyond that basic right-wrong signal.
Precisely. It's the details, the explanations, the examples, the correct answer itself if it wasn't already given in the verification. We're assuming that our brains only really dive into this elaboration stuff after we figured out if we were initially correct.
Makes sense. It's like, first we need to know if we're on the right track, and then we could start absorbing the additional information.
Exactly. Now, you can imagine there are tons of different types of elaboration, right?
Oh yeah, for sure. And the research has definitely explored a wide range of approaches.
It has. But what's really interesting is that despite all this research on different kinds of elaboration, the results on how they actually affect learning have been pretty inconsistent.
Really, you'd think that adding more information to the feedback would always lead to better learning, but that's not the case.
It seems not. More isn't always better, at least not when it comes to feedback. And to make sense of this, the article breaks down elaborations into three main types based on where the information comes from: task-specific, instruction-based, and extra-instructional.
Okay, 3 types. Let's go through them one by one. What's task-specific elaboration?
Task-specific elaborations come directly from the question or task you just completed. So, like, the simplest example is just being shown the correct answer.
Right, so if I got a multiple choice question wrong, the task-specific elaboration would just be seeing the correct option highlighted.
Exactly. Or they might show you the whole question again with all the options, but with the correct one clearly marked. That's also task-specific.
Got it. So it's all about the specific item you just answered. What about instruction-based elaboration?
Instruction-based elaborations pull information from the broader lesson material, but not necessarily directly tied to the exact question you just answered.
So more general background knowledge related to the topic.
Right. It could be an explanation of why a certain answer is correct, or it could be directions pointing you back to the specific section of the text where the answer was.
Okay, so it's bringing in relevant information from the broader learning context. And what about extra instructional elaboration?
Extra instructional elaboration is the most expansive. It brings in information from outside the specific lesson material altogether.
Ooh, so that's where things get really interesting, like real-world examples or connections to other subjects.
Exactly. It could be providing examples that weren't in the original lesson, using analogies to connect to other things you know, or even introducing entirely new but related information to deepen your understanding.
That seems super valuable. You'd think real-world applications and connections to other areas of knowledge would be really helpful for learning.
You'd think so, right? But interestingly, the article points out that there hasn't been a ton of research specifically looking at extra instructional elaboration.
Really? That's surprising. You'd think that would be a rich area to explore.
You would, but for some reason it hasn't gotten as much attention. Now, beyond just the type of elaboration, we can also look at its content in a couple of other ways. Form and load.
Form and load. Okay, I'm all ears.
So form refers to changes in how the information is presented between the initial question and the feedback.
Okay, so like if the initial question was a paragraph of text and the feedback gives me a bullet point summary of the key points, that's a change in form.
Exactly. Or if you answer a multiple choice question and the feedback shows you the same question, but with the answer options scrambled up in a different order, that's form elaboration too.
Interesting. So it's not just about the content of the information, but about how it's structured and presented.
Exactly. And the idea is that by changing the form, making the learner interact with the information in a new way, you might increase how deeply they process it.
It's like instead of just passively reading the correct answer, you have to actively engage with it and figure things out.
Exactly. Now, load, on the other hand, is pretty straightforward. It refers to the total amount of information in the feedback message.
So simple yes or no has a low load, while a detailed explanation with examples has a high load.
Precisely. And load has actually been the main thing that researchers have focused on when studying feedback elaboration. But there's a bit of a catch.
Oh, what's the catch?
The catch is that there hasn't been a really consistent way to measure or define load. Like, what exactly counts as more or less information?
So it's been kind of subjective and inconsistent across different studies.
Pretty much, yeah. So we end up with this general way of thinking about feedback. Feedback, verification plus elaboration, type, form, load, and how the learner actually perceives and processes all of this can be represented as FV plus phi.
Okay, so that's the basic formula. But what does the research actually tell us about how these different kinds of elaboration affect learning? Does more elaboration always equal better learning?
Well, that's the million-dollar question, isn't it? And fortunately, the answer isn't so simple.
Right, because you said earlier that the results were mixed.
They are, yeah. Let's start with task-specific feedback, which is often where the focus on load comes in. Some studies have shown that increasing the amount of task-specific information, like letting learners restudy the correct answer or see all the original multiple-choice options again, can lead to better performance on later tests.
So, more detail, better results. Makes sense.
You'd think so, right? And there's research to back that up. Like Roper found that, and there's a study by Winston and Kulhavi that showed similar results. But then other studies have found that adding more task-specific information either doesn't improve post-test scores or it can even make them worse.
Oh, so it can backfire. That's interesting.
It is. Like, there's research by Fialis and his colleagues and Sassenrath and Young that found these negative or null effects.
So, more detail isn't always better, at least not in that specific way. What about instruction-based elaboration, where you get explanations or are directed back to the lesson materials?
Well, the results there are even more all over the place. Researchers have tried all sorts of things, like explaining why an answer is correct, giving learners rules or algorithms for solving problems, providing written feedback on homework assignments, even having people reread the original instruction. And again, in about half of these studies, the elaborations didn't seem to make any real difference.
So even adding a lot of explanation doesn't guarantee better learning.
It seems that way. Like, Kulavi and his team did a study where they found that even extensive explanations didn't really improve scores on a later test. And there's a lot of other research showing similar results, like studies by Gilman, Lee, Merrill, Cardell and Corno, Elawar and Corno, Peak. Just a whole bunch of studies where elaboration didn't seem to matter that much.
So it's a real puzzle. There's no clear-cut rule for what makes elaboration effective.
That's a good way to put it. It's a really complex area with a lot of factors at play, but there is one line of research that offers a really interesting perspective on this, and that's the work of Tatsuoka and her colleagues.
Oh, tell me about that. What did they find?
They focused on how serious the learner's errors were. Like, was it a minor slip-up or a fundamental misunderstanding of the concept?
So not all errors are created equal. Makes sense.
Exactly. And they looked at how different levels of feedback explanation affected performance on later tests based on the seriousness of the initial errors.
And what did they discover?
Well, they found that for less serious errors, giving more detailed explanations in the feedback did seem to help learners correct those mistakes. But for really serious errors, where there was a deep misunderstanding, the typical kinds of elaboration didn't make much of a difference.
So a little bit of explanation can fix a small mistake, but a big misunderstanding might need a whole different approach altogether.
Precisely. And what makes Tatsuoka's work so unique is that they actually tried to quantify the nature of the errors themselves, which most other research hadn't really done.
So they brought a new level of precision to the study of feedback. That's really cool.
It is, but ultimately the article concludes that we still don't have a solid understanding of exactly how elaboration works on our initial responses, and we definitely need better guidelines for designing effective explanations.
Right, because it's not just about adding more information. It's about adding the right information in the right way at the right time.
Exactly. And that brings us to the heart of the paper, this model that tries to put it all together. The model that combines response certitude with concepts from servo control theory.
Okay, this is the part I've been waiting for.
The
The grand finale, the big reveal.
It's a pretty cool model, I gotta say. It tries to predict not just our final test score, but our actual behavior during the learning process. And it does this by bringing in that concept of how confident we are in our initial answers, that response certitude, along with ideas from servo control theory.
Servo control theory, that sounds very technical.
It is, yeah. It deals with how systems use feedback to regulate themselves.
Okay, so like a thermostat. It gets feedback about the temperature, and adjusts the heating or cooling to maintain a stable temperature.
Precisely. Or think of a car's cruise control. It uses feedback to maintain a constant speed. Now, the authors aren't applying servo control theory in a strictly mechanical way, but they're borrowing some key concepts from it to understand how we as humans process feedback when we're learning.
Okay, so it's a metaphor, but a powerful one. So what are these key servo control concepts they're using?
One of the most important ones is the controlled variable. This is what the system is trying to keep stable. And in our case, as learners, the controlled variable is how we perceive and understand the task we're given.
So like if I'm reading a passage about history, my controlled variable is my current understanding of what that passage is saying.
Exactly. And the system, our brain in this case, is constantly trying to match this understanding with an existing standard, which is our existing knowledge and understanding of the world.
Right, so we're comparing what we're learning to what we already know. Makes sense.
It does. And this comparison happens in what's called the comparator. This is where the perceived stimulus, what we're currently learning, is matched against that internal standard, what we already know.
So the comparator is where we figure out if our current understanding matches up with what we already believe to be true.
Exactly. And the difference between the two, the error in servo control terms, is what drives the system to take action.
So if there's a big mismatch between what I'm reading and what I already believe, that triggers a stronger response.
Exactly. Now, the really cool part is how the authors map these servo control ideas onto the three-cycle feedback model.
Okay, so they're combining these two frameworks. I'm ready for this.
So in the first cycle, when you're initially learning, you're comparing your understanding of the task with what you already know. This leads to your initial response, your answer, and how confident you are in that answer, that response certitude.
Right, so my confidence level is a reflection of how well my current understanding matches my existing knowledge.
Exactly. Then, in the second cycle, you get the feedback. And this is where things get really interesting. You're not just comparing the feedback to your initial answer, but also to your confidence level.
Ah, so that feeling of certainty really matters.
It does, and this comparison between the feedback, your answer, and your confidence can actually modify what you know, update that internal standard.
So the feedback can either strengthen my existing knowledge or force me to revise it.
Exactly. And then, in the third cycle, you see the original task again, maybe on a later test. And now, you're comparing your understanding of the task to your updated knowledge, that internal standard that's been potentially changed by the feedback. This comparison leads to your final response.
So it's a constant loop of comparing, adjusting, and responding. And they actually have a diagram in the article, figure 2, that shows this loop visually, right?
They do, yeah. And it really helps to see how the different pieces fit together. Now, going back to the comparator, its main job is to constantly evaluate how well what you're understanding matches what you already know.
Like a little quality control officer in the brain, making sure everything aligns.
I like that. And if the comparator detects a difference, a mismatch, it signals the system, your brain, to put in effort to reduce that discrepancy.
So if I'm really confused by something, my brain kicks into overdrive to try and make sense of it.
Exactly. And one of the ways we can see this effort is through things like how long people spend looking at feedback. Like studies have shown that people tend to spend more time studying feedback when they've made a mistake, which suggests they're putting in more effort to resolve that mismatch.
That makes sense. If I thought I knew something but got it wrong, I'm going to spend more time trying to figure out why.
Exactly. And this whole system is self-regulating, constantly adjusting and updating its understanding based on the feedback it receives. It's a pretty elegant model, actually.
It is. And you've mentioned a couple of times how important that initial confidence level is, that response certitude. So how does that factor into the model's predictions?
Well, it's actually central to the whole thing. The model predicts that how sure you are about your initial answer heavily influences how you process the feedback and how you perform on later tests, even more than whether your initial answer was actually right or wrong.
So my feeling of certainty matters more than objective correctness. That's really counterintuitive.
It is, right? But there's a good reason for it. The basic idea is that how certain you feel about an answer is directly linked to how well that answer is stored in your memory, how durable that memory is, how likely you are to remember it later.
So if I'm super confident about something, even if it's wrong, that wrong answer is probably deeply ingrained in my mind.
Sadly, yes. It takes more effort to dislodge a confidently held wrong belief than a tentatively held one. And the authors even suggest that your confidence level can be seen as a measure of how well you actually understood the material in the first place. They mention some unpublished research they did that supports this idea.
So my confidence is like an indicator of my comprehension level. That's fascinating.
It is. Now, this leads to the first set of specific predictions the model makes, which is about how long people spend processing feedback.
Okay, so this is about that effort we were talking about earlier.
Exactly. The model predicts that the more confident you were in your initial answer and the bigger the difference between your answer and the feedback, the more time you'll spend trying to understand that feedback.